Let's take a look at how elastic collisions the idea that the total kinetic energy initial, or for interactions, not necessarily collisions, has to equal the total kinetic energy after, and how that can link up with the idea of conservation of momentum in order to give us something useful. Now, this is a ugly derivation. This is something that you do not want to have to do ever, because it'll make you cry. But the final result of it, I think, is something that's pretty important to take a look at. So let's start off with the fact that this is going to be one of those hand of God sort of things where I know exactly what I want to get out of these two equations, and somebody else has already done a bunch of this work, and I've done it before, and we know, all right? We know what we're doing. So there's going to be some sleight of hand. There's going to be some substitutions that you wouldn't have normally done, but they're all going to be for a purpose. Let's start off with the idea that if we have a collision between two objects and it's going to be elastic, on the initial side, it has to be two separate objects. We have to have object 1 moving, maybe object 2 is sitting still, and then after the interaction, maybe object 1 is moving backwards and object 2 is moving forwards. But we don't know their velocities. And if we don't know both of their velocities, we're running into a bit of a problem. If we just have the initial conditions for object 1, but no information about the end, there's too many unknowns. And too many unknowns is going to cause us to not be able to solve the problem. So if it's an elastic collision, we know that energy is conserved as well as momentum. But we also know that from that conservation of momentum, the idea that when two things interact at that point of contact, there's going to be equal and opposite impulses. And if there's equal and opposite impulses, if I say that the j on object 1 is equal to the negative j on object 2, then that means that the change in momentum for object 1 is going to be the opposite change in momentum for object 2. So one gains momentum, the other loses it, or has it subtracted from it. In this case, object 1 is going from a positive momentum to a negative, and so that would be a negative delta p. But object 2 is going from 0 to something positive, so the opposite of a negative would be a positive. And so that equation makes sense. And we want to further make sure that we make notes that delta p should be the mass of the object times its change in velocity. Go ahead and add in all the subscripts here, v1f minus v1i. And this is going to be key. This is going to be a very important thing to plug in, because we're always going to run into this idea of having too many unknowns for our equations. So let's put that in our back pocket. I apologize, I got a little bit of sniffles right now. Let's start with the conservation of energy. We would have 1/2 m1 v1 I squared. I'm going to leave the vector hats off here because it's going to be a bit cumbersome. 1/2 m2 times v2i squared should be equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Here we can go ahead and cancel out the 1/2s. Don't need them. I'm not going to rewrite the equation just yet. But if we've got that, we're getting close to what we need to do. But we've got all of the object 1 values on one side and the object 2 values on the other. In order to get something that can utilize this formula, we have to have all the 1s on one side and the 2s on the other. So let's do a little bit of moving things around. I'm going to take this and move it over here, and that and move it over there. And I should have m1 v1i squared minus m1 v1f squared. And then the same thing on the other side. So we got rid of the 1/2, we got rid of the separation of the 1s and the 2s. Now comes the tricky part. I'm going to go ahead and factor out the m1, because looking back at this, we got the m1s outside of some v1s and v2s, so let's see if we can get something that looks like that. And it's not looking quite like it, right? We've got the m and then some difference of v's, but if we go back up to the momentum thing, they're not squared. These terms here are not squared, but down below they are. So here's where we have to do a little bit of that old math stuff that you remember. Remember factoring? When we factored, if we had like x squared minus y squared, we could say that that was equal to we do x plus y times x minus y. That math trick is what we're going to have to do here, because that'll allow us to get a difference in terms that are not squared. And that's going to allow us to substitute up above. So, more math, or at least algebra in this case. So I can say this is m1 times, let's see, v1i plus v1f times v1i minus v1f. And on the right side, m2, v2f plus v2i, and v2f minus v2i. Again, this is that I know what I'm supposed to do situation. No high school student is just going to decide to do all this math on their own, or maybe they will. Hopefully they have friends as well. So we're at this point, and here's where I can start picking apart and noticing that I have some similar things. I'm going to switch colors up here. Up above, see if I can get all this on the screen at one time. I've got M1, okay, and then I've got V1F minus V1I. Well, I've got the V1F and the V1I, but it looks like the sign is backwards. And then on the right-hand side, I've got the M2, and I do have V2F minus V2Y. So it looks like I've got everything on the right side of the equation I need to match up with what I've got from the momentum equation above, which, by the way, we're gonna try to say two things are equal and we can just cancel them out. But what if I took that negative sign and I moved it over here and applied it? If I applied that negative, I could negate everything inside the parentheses. And if I negated everything inside the parentheses, I would then have the V1F has a negative sign on it, and the V1I is positive. Meaning that the things I've highlighted in blue and yellow down below here are equal to each other. And if two things are equal, you can divide them away out of the equation. So in order to make that a little bit clearer though, I'm going to go ahead and move this out to the front, and I'm going to pull the negative sign out. So I'm going to have M1 negative, and then I'm going to switch to the order of the V1F and the V1I. And then leave the V1I plus V1F. And then over here on this side, I'm going to write things in yellow as well. I'm going to move this over to the front and leave the signage the way it is because that's what I want. And write this part in black. And from up above, we said that this term, which represents the delta P for object 2, and this term looks like it's negative delta P for object 1. Sorry, I said I was going to not put the hats on there. Those two are equivalent. And if they're equal, they can cancel out. So that leaves us with just v1i plus v1f equals v2f plus v2i. Now the order of these from side to side doesn't matter, but this is saying that the total velocity, or the combined velocity of object 1 before to after, has to equal the total velocity of object 2 before to after, which gives you an additional equation in which to solve problems. Not necessarily the most kind of fluid idea, but it still works. Alternately, we can move it around so that the initial values are all on one side and the final values are all on the other, which would give us v1i minus v2i equals v2f minus v1f. And if we kind of like the idea of having finals minus initials here, we can move those around and put a negative sign in front and say it's v2i minus v1i equals v2f minus v1f, which is kind of a useful formulation here. What we have up above is saying that if you add up the velocity before and after for each object, it should be the same, which is nice. But down below here, this is saying that the relative velocities of the objects are opposite from before to after. This term right here is the relative velocity between 2 and 1. And that's the initial side. Over here, it's the difference in their velocities. These are the relative velocities as well. And they're opposites. So if object 1 is moving to the right at 2 meters per second in the beginning, and object 2 is at rest, I guess I put that right here, we would have 0 minus 2, we'd have a negative 2. On the other side then, if we were to figure out what was happening, we would have to have a difference of velocities of negative 2. So the object, maybe the object 1 is really light and it's going to be going fast to the left after the collision, then we'd have a small v2f minus a large v1f, and we would get a negative relative velocity. So these are two ways of looking at elastic collisions, but these equations are key to give us a little bit more information as to what's going on.